Okay, hello everyone. I really appreciate being with you all. Today, I'll give a brief introduction to the graph database and share our experiences from implementing a graph database based on PostgreSQL. Before starting, how many of you are familiar with graph database? Okay. First, let me introduce myself. My name is Ki-Sung Kim, and I am a CTO of Bit9 Global. I received a doctorate degree for researching graph query optimization, and before joining the Bit9, I had developed a distributed relational database system in Tmexsoft. Now, I'm leading the development of a new graph database system called AgensGraph in Bit9. Okay, what is the graph database? It is the one category of NoSQL DBMS. Graph database is an optimized system for handling complex connected data like social network and supply chain management. But the graph database usages are not limited to these network data. Graph database uses the graph data model. What is the most different thing of the graph database is that the relationship is the first-class citizen in the database system. In other words, relationships are explicitly managed and handled directly by the database engine. In relational databases, relationships are created and handled implicitly. The data is managed as a row of a table and regardless of whether it is entity or relationships. In the relational database, every data is a row. And if we want to retrieve some data, usually we should join the related tables by ourselves. The database does not provide any facilities to handle the relationships. But in the graph database, you can create nodes and relationships explicitly, and you can query in terms of relationships. So we can make our data more connected, and the management of the connected data becomes much easier in the graph database. So graph database handles data in different views from relational database, node and relationships. It is very similar to the entity relation model, so it is very intuitive and easy to understand. Gartner says that the graph database represents a radical change in how data is organized and processed. For more concrete examples, I want to introduce Cypher query language. The Cypher is a declarative query language for the property graph model. It is inspired by SQL and Spark, and it borrows many clauses like where and order by from SQL and the graph pattern matching from the Spark. The Cypher is developed by Neo4j, Neo technology, since 2011, and now its newest version is 3.0, and it is still actively being developed. This is a Cypher example. As I already said, in the graph database, the queries are made in terms of nodes or relationships. These Cypher queries make two nodes whose labels are person and company, respectively. And this part is to specify their property values, like this. And you can specify any key value properties for nodes and relationships. And after executing these two queries, then there will be two nodes exist in the graph database. And then you can create a relationship between these two nodes using this query. So after executing this query, there will be a new relationship between these two nodes. And you can query the graph data using the graph pattern. In Cypher, graph patterns are represented as an ASCII code style diagram. This is to find the company Ki-sung Kim worked for. And you can see this pattern in this match clause looks very similar to these diagrams. Also, you can specify variable length relationships like this. If you query using SQL, you must use the recursive common table expression, and the query will be more complex. As you can see in this example, there is no need to define table schemas, and you don't need to use join operations when making the query. So queries become very concise and easy to understand. Sorry. Here is an interesting real-world case about the graph database. This is a blog post from Hippo Labs. Actually, this blog post is about going back to Postgres from a graph database and MongoDB. They developed an image application using Neo4j and MongoDB. They used MongoDB to store image data and used Neo4j to manage the category metadata for images. But as the size of the data increases and the application logics were getting more complex, the Neo4j became slow. And they say managing two databases was painful for them. So they decided to integrate their two databases into PostgreSQL, and it gave them pleasure. But the writer said that the Cypher query language is very concise and easy to maintain. I want to emphasize this point. From the same idea of this blog, we had thought that it would be very valuable thing if we can provide graph data features in the relational database system. So we started to develop a new hybrid database system called AgensGraph. We think that hybrid database will be a future trend. Already, PostgreSQL is a kind of hybrid database because it provides NoSQL features like JSON data type. Gartner also says that by 2017, all leading operational DBMS will offer multiple data models, relational and NoSQL, in a single DBMS platform. And we also have seen several advantages and possibilities of the graph database. So we decided to make a new database integrating the advantage of the graph database and the relational database systems. What we want to develop is a hybrid engine for graph and relational model. And more specifically, we want to provide the Cypher query processing on Postgres. It will be an online transactional graph database, and it will provide a disk-based persistent graph storage. Rather than developing from scratch, we chose to develop our database using PostgreSQL. There are many reasons to choose Postgres among other databases. First of all, as you already know, PostgreSQL is a fully featured and enterprise-ready open-source database system. There is no license problem for using Postgres code, but this is not the only reason. There are also many technical reasons for our choice. First, graph processing actually uses relational algebra. Whatever storage layouts are used to store graph data should be stored in disk as serialized like tables. And the graph traversal step is in principle a join operation. Even Neo4j uses the relational operators like hash joins. You can confirm this by examining a Cypher query plan in Neo4j. So it is not abnormal to implement a graph database on top of a relational database engine. And the graph pattern matching is usually complex join query. So the query optimization is very important for the graph database system. And PostgreSQL has already a great query optimizer. Finally, there are abundant ecosystems of PostgreSQL. So if we implement our graph database using Postgres, we can exploit these extensions too. However, there are also many challenges to implement a graph database in PostgreSQL. First, we need to design efficient storage engine for the graph data. It should be efficient for graph pattern matching, which is very I/O-intensive job. There are several proposed methods from academic research, but these are mostly assumed read-only environment. And our goal is to make a OLTP graph database. So the storage engine should be efficient for both reads and updates. And the processing of the graph pattern matching is the most challenging part. The graph pattern matching can be handled using the join operations, but it is not the end. There are several complex issues like variable length path query and shortest path query. Moreover, there exist mismatches between graph model and relational model. And finally, because graph queries involves many joins, cost estimation of the Postgres could be inaccurate. So we cannot rely on only PostgreSQL's query optimizer for the graph query optimization. We need a new cost estimation model specialized for graph query patterns. I cannot deal with all these issues in this talk, so I focus on the storage design issue in more detail. Let's move on to the internal of the graph storage. Graph data is stored in disk as decomposed into vertex and edges. And when processing the graph pattern matching, the decomposed vertices and edges should be combined. When traversing a graph, given a vertex, we should be able to find adjacent edges and then follow the edges to find another adjacent vertices. So it is essential to find adjacent vertices and edges efficiently when processing the graph query. Now, I saw two graph storage examples, Neo4j and Titan. Neo4j and Titan are the most popular graph database. Neo4j is developed by Neo Technology and its latest version is 3.1. Neo4j supports Cypher query language and uses fixed size record array. Titan was developed originally by Aurelius, but they were acquired by DataStax last year, so the name is changed into DSGraph. Titan is a distributed graph database, and they use other NoSQL databases like Cassandra or HBase as their backend storage. Now let's look into the Neo4j storage. In order to find adjacent vertex and edges, Neo4j uses the direct pointing method. They store graph data in fixed size arrays for nodes and relationships. This is the internal representation for nodes and relationships, and this nodes element has a pointer to adjacent edge list. And the relationship adjacent to a node are organized as a doubly linked list. And a relationship element has two pointers to the start and the end nodes. This fixed size record is only for nodes and relationships pointer information. The property values, which are of variable size, are stored separately outside these arrays. Neo4j calls this structure as index-free adjacency because they do not use bit-tree index. And the search complexity for adjacent nodes or relationship is order of 1 because they are accessed by direct pointer to disk location. Titan has a different structure. Titan uses other NoSQL systems like HBase or Cassandra, And they store the adjacency list for vertex as a long row or a value in Cassandra. The adjacency list of a vertex is the list of the edges which are connected to the vertex. Vertexes and their edge list can be found by a key vertex ID. Edge list can be very long if there are many adjacency edges to a vertex. And because the list should store all connected edges, one edge must be stored twice in Titan, in incoming edge and as an outgoing edges. In AgensGraph, we take a different approach from the previous systems. In fact, we could not use the fixed size array approach in Neo4j because in PostgreSQL, tuples are moved when they are updated. So we cannot fix the location of a vertex and edge. And we think that the fixed size array approach is not very efficient for OLTP workload. And Titan's approach is for the distributed NoSQL system, and it is not very proper for online transactional system. This is the current storage structure of AgensGraph. We use the heap storage of PostgreSQL for vertex and edge store, and vertexes are stored in two-column tables, and edges are stored in four-column tables. And for efficient search, we used B-tree index for vertex ID and edges start and end ID. But current storage layouts have several issues. First, we found serious size problems. It is mainly because we made composite indexes for edge tables. If we made indexes for single column, then single column start or end, we could reduce the index size. But in this case, we cannot use the index omniscans. Moreover, because there are many duplicates on start and end ID, if we using gene index in PostgreSQL, we could reduce duplicate keys. But if we choose this layout, again, we cannot use the index omniscans for the graph traversals. And due to the nature of the Postgres index, if the property values of an index is updated, then all related indexes should be inserted. So it is not good for the OLTP. I know the indirect indexing is being discussed in PG Hackers, and we need the same similar features in our AgensGraph. Currently, we are developing a new index mechanism to resolve these issues. We should reduce the size of the index and at the same time, we should be able to use the index omniscans. And indirect indexing mechanism is also needed. This is our new index structure for graph traversals. Rather than maintaining two composite indexes, we only need one index on single column. And to reduce the sizes, the index uses a bucket structure. And for the indirect indexing, this index stores edge IDs rather than TIDs for edges. And if we retrieve edge IDs from this index, then we need to access the edge property, then we use the edge ID to search the property values. The property table will be scanned only for accessing the property values. So traversal on graph can be conducted accessing only this index structure. And updates on property values does not affect this index. In addition, this index structure need not to be B-tree index. So we will test also hash index, which are currently being developed in Postgres community. And another features that our other graph database does not provide is the label hierarchy. In AgensGraph, vertexes and edges are grouped into labels. And you can create vertex label, and edge label. This can provide different storage options for each labels, like table space. And you can make a label hierarchy by using inherit options. In this example, there are 4 vertex labels, and the comment and post are child label of message labels. Using this feature, users can manage vertex data in more structured manner. Last month, we released AgensGraph 0.9. You can clone our project from GitHub or download from our homepage. Using the current version of AgensGraph, you can create graph objects and vertices and edges. We implement about 70% of OpenCypher spec. And one of the most important features is the integrated query processing. You can make a query using both Cypher and SQL. And we also provide JDBs, ODBs, and Python client driver. And server performance monitoring and graph visualizations are provided by using Tadpole DB Hub. And I want to introduce an open source web-based DB imaging tool, Tadpole DB Hub. This is an open source project which is being developed mainly in Korea. Tadpole is a unified management tool which supports several databases, including PostgreSQL, MongoDB, Oracle, and AgensGraph. We implement a real-time server monitoring feature and Cypher query browser graph visualization in Tadpole. And this is the screenshot of the Tadpole for AgensGraph. This shows an example for graph visualization. You can execute a Cypher query in Tadpole, and the result graph are visualized like this. And you can explore the graphs by double-clicking a node, and then you can dynamically expand the graph. This is our future roadmap of AgensGraph. Most importantly, we plan to extend AgensGraph to a distributed system using PostgreSQL. And we are developing specialized storage and indexes for graph data. And we also found JSON overhead for property values is significant. So we will developing a compression method like JSON. And to improve the query optimization, we will develop the graph query optimization using the graph statistical information. Lastly, we will provide integration with Hadoop system and graph analytic systems like GraphX. AgensGraph is an open source project, so if you are interested in the graph database, please join us. And we have benefited from the great Postgres community. So I wish someday we could contribute the Postgres community again. And Bit9 hosts a meetup for the graph database in Silicon Valley. So if you want to get more information, you can visit our meetup too. And this is the end of my presentation. And thank you for your attention. And any questions? Yes?
Do you compare performance with Neo4j?
We are currently working on the benchmarking. We are using the LDBC benchmark tool for the graph benchmark. So we have implemented all the benchmark drivers to benchmarking for AgensGraph. Soon we will run the test. Yes. Yes.
Is there a way to convert from Neo4j data to this, and do you have a size comparison? How big data?
Yes. As I already said, there is still big size problems, and currently, we are using the naive structure for the graph indexing, so the size is double of the Neo4j. So we expect that if we after we implement our new index structure, then we can reduce the size overhead. Yes.
How's your, is there any schema?
Schema. There is only schemas for label. Users only need to make vertex or edge labels, and all properties are stored in JSON data type. So the property values are schemaless. And you can store a JSON document in vertex or edges. It is unlike the Neo4j. Neo4j only supports the key value stores. Yeah.
And data would need migrated from Postgres. This wouldn't operate on your existing data set.
Sorry.
You wouldn't be able to use this with your existing data in Postgres. It would still be a migration from Postgres.
Okay. There are Cypher clouds for data importing, load, and we implement load clouds to import data from relational schema. So we can use load clouds to import data, any Postgres relationships. And if you use the foreign data wrapper, then you can import data from other external database systems. Yes. Yes.
Are there any use cases, customer use cases, are you optimizing your development process, or are you trying to make this AgensGraph as common use as possible?
Okay. We are hoping to AgensGraph will be used in common use case, and in Korea we doing a project using Graph database to detecting cyber attack in internet system. So it is very complex network data that connects the routing and proxy servers, and it is very connected data. And the customer complains that relational database is too slow to executing the query on the network data. So it is very good use case. Yeah.
So one more question. For example, you have mentioned that, for example, Titan is a distributed graph database, and distributed systems in graph databases is a very common use case. So are you planning to make it as distributed PostgreSQL-based graph database as well?
Yes, we definitely have a plan. And currently we are considering the PostgreSQL, and we also considering the PG shard of the Citus data. Yes. No more questions? Okay. Thank you very much.